So let's go ahead and derive the chain rule for derivatives, single variable. Okay. Okay, good. So the claim is that if we'll say p of x is equal to f of g of x, so this composite function, f composed of g composed of x, then p prime of x is going to be equal to f prime of g at x times g prime of x. Okay. Now there is admittedly a quite easy proof involving the Leibniz notation, which we're not going to be using here because the Leibniz notation is based on the limit definition. So the purer definition is that which is based on the limit definition. That's what we're going to be going for here today. Okay, using just the limit definition of the derivative. Let's go ahead and dive into the proof. Okay, using the limit definition, p prime, we're just going to build this thing up from the ground, is equal to the limit as h trends to 0 of p of x plus h minus p of x over h. Okay, which is of course just the limit as h trends to 0 of f of g of x plus h minus f of g of x over h. Okay. Now, at this point, I kind of want to try to manufacture a g prime of x. Let's see. Yeah, what I'm going to do is multiply top and bottom here by g of x plus h minus g of x. See if I can zoom out and, no, I'm just going to go down this line. That's fine. So we have a limit as h trends to 0. We're going to have f of g of x plus h minus f of g of x over h. But now I'm going to multiply top and bottom by g of x plus h minus g of x. Top and bottom. This is just one, right? And don't think that we have any concern about division by 0. We don't. The limit is not concerned with what happens at 0. It's concerned with what happens near as we want, as long as there's a neighborhood of definition around 0. That's specifically the mathematical definition of the limit. As long as there's a definable neighborhood. Again, I can let h get as close to 0 as I want, and this denominator is never going to actually reach 0. So this is a valid operation here. There's nothing's being violated by this. It's just 1. Anything divided by itself is 1. Now, I'm going to switch out these denominators because, as you see, g of x plus h minus g of x over h, the limit as h goes to 0 of that is g prime of x. I'm going to be using the algebraic property a over b times c over d equals a over d times c over b. Kind of goes without saying, I suppose, but it's these little properties that are seemingly insignificant that serve as the basis for abstract algebra, that serve as the basis for our most eloquent and seemingly complex proofs. It's really not that bad. All I got to do is switch these out. Okay, so I've got the limit as h trends to 0 of f of g of x plus h minus f of g of x, okay, divided by, now I'm going to switch these out as I said, so this is now divided by g of x plus h minus g of x right here. And then over here I'm going to have g of x plus h minus g of x over h. Okay, now admittedly this is g of x plus h minus g of x over h, not the limit as h goes to 0 of g of x plus h minus g of x over h. But remember that it actually is, because the limit of a product is the same thing as the product of limits, right? The limit of a product is the same thing as the product of the limits. Isn't that nice? In fact, these limit properties are exactly as we would want them to be, right? Limit of a sum, same thing as a sum of limits. Limit of a difference, difference of limits. Limit of a quotient, quotient of limits. Provided that, right? Provided that the denominator is not equal to 0. Okay? Limit of a product, product of limits. Okay? Just as we would hope. It makes sense that it would be that way because the limit is not concerned with what happens but what happens near. So I can take this and consider this as actually the limit as h trends to 0 of f of g of x plus h minus f of g of x over g of x plus h minus g of x times the limit as h trends to 0, right, using this property of g of x plus h minus g of x all over h. And look at what we have here. This is g prime. Okay, so we're essentially halfway done. We've forged this factor g prime of x. Okay, so we've got the limit as h trends to 0 of f of g of x plus h minus f of g of x over g of x plus h minus g of x times g prime of x. How convenient. Now, let's use a substitution to try to make this more evidently look like f prime of g. Now, if you're clever enough, you can see that it already really is, and you can kind of rest your case here, but we're going to make it more evident. Let's let u equal, and we're going to be switching limits as well from h to u. So we want this whole thing to be one variable, just like we had division by h, right? Let's let u equal g of x plus h minus g of x. That would seem like a convenient way to do this. Okay, now, what is the limit as h trends to 0 of g of x plus h minus g of x? What is it? Well, it's going to go to 0. Okay, it's going to go to 0, but that's the same thing as the limit as u goes to 0 of u. Okay, think about that for a second. It's all 0. The limit of this is 0, the limit of this is 0, the limit of this is 0. So I can go ahead and switch things out. I can say, well, okay, this is equal to the limit now as u goes to 0. What is f of g of x plus h? Well, that's just f of something, and g of x plus h is just u plus g of x, right? I can solve for g of x plus h by adding g of x to both sides. So it's going to be f of, and I'll write that as g of x plus u, okay, minus f of g of x. Starting to look nice, isn't it? Over u times g prime of x. Okay, now what is this? This is just f prime of g. So we're done. Okay, we've got f prime of g of x times g prime of x. So that wasn't really that bad after all. Of course, using the Leibniz notation, it would be even easier. Oops, there we go. Using Leibniz form, of course, we can just swap out differentials. But we're not going to do that. Remember, the Leibniz notation is shorthand, shortcut notation, as it were, for the actual derivations, right? The actual derivative, which, of course, is defined using limits. Hope you like that. Let me know if you have any questions, comments. We love proving math. We love proving anything, quite frankly. Physics, chemistry, whatever you need proven, you just let us know. We try to stay as busy as we can. Sometimes we get a little sidetracked with life. Hope you can enjoy this, and hopefully you enjoy all mathematics going forward. Have a great day.